Hello, hello. Right, I'm James Tagg from Valis, and we're going to kick off this afternoon with physics of consciousness. We have three speakers, myself, Stuart Hameroff, and Rajneesh Khanna. And our running order was I'm going to talk initially about the some of the hard physics of consciousness. Stuart is going to talk about the hard biology of consciousness. We'll have a little bit of a break. And you can ask Stuart some questions. He has an enormous background in this field. Then we're going to talk about photobiology and whether plants might be conscious or what they do that looks like us. And then I'm going to talk to you a little bit about my company and what we do and the fact that we send brains to space. And then we'll have a panel. You can ask us questions. So what is consciousness? Well, this experience we have here, this is consciousness. And you know, the only working definition that we kind of like is that it's what goes away with anesthesia. That's Stuart's definition. Some people think it's a delusion. Dave Chalmers is very famous for one of Stuart's conferences, getting up on stage with a hairdryer and pointing at the audience. I had someone make me a miniature version earlier and actually point at the audience and say, right, are you conscious? Yes, no, yes. I won't actually point out any of you who are not conscious because it's a bit rude. But, you know, we just don't have a method. And we really don't have a method. So we don't have a definition. There's 400 competing definitions for consciousness. We don't have an objective measure, which is a bit worrying if you go into an OR, because the anesthesiologist is going to, I can never say that word, is going to put you to sleep, but they're not sure that you are asleep. So it's an art as opposed to a science. They do it with a great deal of experience. There's obviously a joke, which is that if you start a conference on consciousness and decide that your first point of order is to define it, you will actually not have a consciousness conference. You will just talk about the definition, because it can go on forever. But let's talk a little bit about Roger Penrose's, let's say, pseudo definition of consciousness. He doesn't really talk too much about consciousness. But it's that consciousness, this thing that we have in our brain, and this experience we have, must be for something, right? It takes some effort to do it. We evolved it. Why on earth would we evolve it and go through all of that, paraphernalia to get this ability if it doesn't do something useful? Roger Penrose, very famous for inventing the black hole. Penrose triangles, the stairs in movies are his. Penrose diagrams, if you look at space-time diagrams, those are all Penrose diagrams, and the more Penrose matrix inverse. So when you do AI and you solve a matrix, you're using Roger's maths. He also makes these very beautiful tilings, and sorry, this is going the wrong way. Yeah, he also makes these very beautiful tilings, and so the Transbay Transit Center here is covered with one of his tilings. This was the opening of the Transbay that we went to. He wrote two books nearly over 35 years ago, called The Emperor's New Mind, where he said, well, our explanation of what's going on in the human mind is incomplete. And the main reason he sort of started off with this is that his perception was that he does things that computers could not do, and that these tilings that he invents are a branch of non-computable maths. And so he's clearly doing non-computable maths, and computers can't do it because it is by definition non-computable, and so there's a problem to solve. It's a very interesting problem. It's always been an interesting problem. It's much more interesting now because we're seeing computation, improve with Moore's law, and now it's kind of tipped over this boundary where you can do AI with it. And so now we are actually getting computers that are going to rival us. And the question is, are we, as Steve Wozniak says, going to become like dogs to humans, but humans to AIs, but we're just their pets, or is there some fundamental difference between them? So let's talk a little bit about the physics. So I'm just going to define physics as the application of mathematics to understanding the universe, for want of a better reason. And modern physics is sort of three main theories: quantum mechanics, relativity, and computation. Now, computation is often not thought of as one of the theories, but it's one of the defining theories of the last century that explains why we're here. Interestingly, of course, at the turn of the last century, Lord Kelvin said, oh, we've done with physics, right? All science is done. We've discovered everything we need to do. All we need to do is now do a few experiments to get all of the parameters precise. And then, of course, annoyingly, 5 years later, Einstein, came up with relativity. I should point out that he didn't single-handedly do these things. There were a lot of other people involved, but he's a giant. A team of people came up with quantum mechanics, and then Gödel and Turing, a little bit later in the century, came up with the incompleteness theory, which explained mathematics and computation. So normally I'd do it the other way around, but I'm going to start with computation here. So for computation, we had an equivalent to Lord Kelvin in computation or mathematics called Hilbert, and he thought that basically mathematics was going to be complete. It was a project he could finish in his lifetime. There were basically two important books. There's Principia, which was Newton. There's Principia Mathematica, PM, which was this Russell Whitehead set of books that takes 100 pages to explain that 1 + 1 is 2. But he figured that if you wrote another 8 chapters or 8 books, all maths would be done, completely done, right? And that was his project. And then annoyingly, Gödel turned up with his doctoral thesis and said, no, mathematics is incomplete. So you can have statements in mathematics that are true, but can't be proven within that system. And this is actually the most important feature of this. So I will actually try and explain it properly, although every few years I explain it properly, and then I look back at my slides from 5 years ago, and I realize my proper explanation from then needs some improvement. But basically, Gödel said Hilbert's wrong, right? And you have to think about how the mathematics you have relates to the real world. So the best example of that would be geometry, the Euclidean plane. You go to school, you learn that triangles, have angles, they all add up and so on. Well, that's not true if your triangles live on a curved surface. And the only way you can decide whether it makes sense for your triangles to live on a curved surface or a flat surface is by telling the mathematical machine, I think it makes sense to use this geometry here. Mathematics can't work out what the universe looks like. You have to tell it. And this is the fundamental problem. So computation, we used to compute. In fact, you can still hire computers, I think, around the world. People just would add up. We all learn computation at school with just long multiplication. And what Turing said is there's a way of making a machine that just does any possible conceivable computation. This chap actually had that tattooed onto his calf. So in principle, that little machine, that little state machine, will compute anything that any computer language we have, any quantum computer could possibly do. It'll be horrendously inefficient and probably painful for him if we're jabbing his calf. But it's a very, very simple, computation is very simple. And then Turing asked this question. If you've watched the movie, it's the unpronounceable theory, the Einschlussendgens, the whatever theory, right? Which is, will a computer always halt, or will it sometimes crash with a blue screen? And there's lots of questions you'd like to ask a computer. Should I marry this person? Should I do this? Should I do that? Is it possible to guarantee you can answer the questions with a computer, or is it not? And the answer, it's not. And Turing just created this very simple idea. So he first had to invent the computer, of course, in his paper. And then he had to show that if you invented that computer, you could do a similar paradox like this statement is a lie, right? The problem with that, this statement is a lie is it's true and it's false, and it blows up in itself. So he created a fairly simple kind of argument with a computer and said, right, based on this argument, computers are not going to be able to halt. And there's a Russian mathematician called Matsievich who took his work on a lot further. But he gets up and talks to students and so on. They say, but surely I can write a computer program that, I can write it and it will either say yes or no at the end. And he says, did your computer ever crash? Right? So if you can program a computer to say yes or no, 0 or 1, to any problem you give it, sometimes it will output 3, and sometimes it will never stop. It will blue screen, right? If you have a watchdog watching it, and you say, okay, you've not done anything long enough. So Turing, basically said computers are incomplete. There are things that they can't do. And this is Roger's point, which is our brains appear to do things that are non-computable that, by definition, a computer can't do. So let me try and explain exactly why that is. So, mathematical proofs are sort of axioms and rewrite rules. So the simplest rewrite rule you can explain to someone is a matchstick puzzle. Right? Move a matchstick and make this equation work. You understand the rules, right, of mathematics. They're very, very simple. Kids, of 5 can do this. And you understand the rewrite rules. It's very, very simple, okay? And what Gödel says is that you have systems which have axioms, like the rules. You can rewrite this. You can move matchsticks in the following way. And then you can prove different things. What you can't do is come up with a new axiom, right? Because a new axiom would extend the mathematical field. And the incompleteness theorem says you can't do that, right? And it's quite subtle. So I always used to think that the problem was that you'd add in an axiom and it wouldn't work. You'd put it in and you get syntax error. But that's not the case. What happens is that there are an infinite number of axioms you could choose to add. Some of the axioms will give you a syntax error. They are very easy to remove. Some of the axioms won't give you a syntax error. They make sense. They make sense to mathematics, but if I show them to you, they make no sense. And that's the Euclidean plane argument. If I show you a piece of graph paper, you look at that and go, oh, we're going to have to use flat Euclidean plane mathematics. You just know it, right? But you have to be told. So the thing about proofs is computers can do a lot of them. Now, this is a huge area of argument, and really the person who sort of dominates this argument is a chap called Harvey Friedman, and he has this grand conjecture. And what he says is, you will never see a proof in your life that you couldn't simply have created with very, very simple mathematics. Now, I quite like his argument, although he's basically saying what I'm talking about is nonsense. Quite like his argument, because he's saying, yes, there are theoretically these esoteric things that would be outside a computer. So they do exist, but we'll never see them. We don't care about them. He's also saying, interestingly, that there could be some things in that class that actually you can compute with very simple rules, but it would be fantastically computationally expensive to do so. So there seems to be the two things that happen with non-computation. One is there are in principle things that computers can't do. I think that there are a lot of the things that we actually see today, but some people disagree with me. And then the other thing, of course, is that being able to do non-computation gives you shortcuts. You could do a problem in a millisecond that if you had to compute your way through it would take you, trillions of years. And you can do that because you can just look at it and go, oh, it's obvious that I should add this rule. It's an obviously safe rule, and it lets me short-circuit the problem. And so this has been applied. There's lots of proofs out there that you can demonstrate are non-computable. So the four-color conjecture, as I learned it as a kid, is now a four-color theorem because it was proven. That's outside the capability of a computer to do. And you can actually now go to ChatGPT and say, list me all the proofs that are out there that required an axiom to be added that's not inside piano arithmetic in order to prove it. And it'll just spit you out 50 or 60 well-known mathematical proofs. So I go, okay, that's pretty interesting. I better phone up Harvey Friedman and go head-to-head with them. I haven't done that. I did go head-to-head with Aronson, and I failed dismally during COVID. But I think I've got my arguments a little bit more clean now. And so what you have is this non-computable zoo, right? You have a bunch of types of problems that are in principle non-computable, and a bunch of problems that are easy and known and computable. And that's similar to the computability zoo, if you're into computability. So there are some things that are very easy, some things are fabulously difficult. Everyone's very interested to know whether P equals MP. They're also very interested to know that something like ECDSA, the quantum Bitcoin algorithm is very difficult for classical computers and trivially easy for quantum computers. So there are things on this map that change. So what we're really talking about here is if you've got a non-computable machine, you can do things in very, very quick time that otherwise would be computationally incredibly hard. So you get through this idea that you've got non-computation going on, and then you say, well, where would the physics be to support that? And the problem at the moment is we live, according to most physicists, in a block universe, right? There's a block of space-time. We simply live at a dot in space-time, and there is no flow of time. There's no reality. It's all predetermined. And the reason that you can remember what you did yesterday is simply in this moment in space-time, what you did yesterday is in your head, right? It's just a complete illusion. That's why I was saying a lot of people at the moment think consciousness is essentially an illusion. We either live in a simulation or we live in a simulation. The only question is, do we live in a simulation running on the computational fabric of our universe, or do we live in a simulation running on a big computer that Elon Musk built in a previous lifetime that we're now running through? That we live on a computation. There's just three problems with it. The first thing is general relativity seems to argue that in black holes we destroy information. If we destroy information, we don't have a nice linear evolving universe. Second thing is, and I would argue, is brains appear to create information. We are creative, we use this non-computable faculty, and we reorganize things in a way that creates information. You couldn't have simply computationally made it happen. We have lots of arguments about it, but yeah. And then the final thing is, quantum mechanics and general relativity have a big inconsistency in them. They really don't work together. Roger just says, okay, well, you could have a many worlds, right? Each photon that comes into a glass of beer, there's an 8% chance of reflecting off a glass surface. So, 8% of the photons reflect, 92% go through. In fact, each photon goes through and comes back, and it doesn't actually decide which it did until it hits our eye, right? And he says, okay, so one of the arguments for that is the photon splits. The universe splits. There are two different universes, one where the photon went through now, and one where the photon didn't go through, right? And that's an argument that the majority of physicists today probably believe in, right? And the majority of people that I talk to say, that happens. Roger points out the biggest problem is we don't see the other universes, right? We should see the other universes. At least we should see their gravitational signature. If there's two different universes with a dead cat and a live cat in each of the universes, and one's lying down on the floor and one's standing up, we should feel that gravitational effect, because gravity doesn't obey quantum mechanics. It's a classical theory, so it doesn't obey it, so we should feel it. We should be able to detect it. We should see abnormalities caused by it. So as Roger will explain, the Penrose theory and how that actually causes collapse and so on. But these are the three big puzzles, and we could argue that there are lots of other ones in physics, but these are the big puzzles that we have at the moment with physics that say it's not quite as simple out there as we might think. So that's the end of my first session. I'm going to talk about actually trying to build one of these machines a bit later, but we'll now move over to Stuart, who's going to talk to us about consciousness. Not that I didn't just talk about consciousness.